Welcome to MathMuni. Dalzell's integral was conceived in 1944 by a British mathematician, D.P. Dalzell. It is a fairly straightforward integral, as we shall see soon, but what makes it special is how it unexpectedly leads us to two very interesting results relating to the value of pi. Along the way, we get some practice in polynomial division. So let's get started. To begin with, note that if you open up the polynomial in the numerator of the integrand, the highest power of that polynomial is 8. And in the denominator, the highest power of the polynomial is 2. So the natural first step would be to go through the polynomial division and see if it results in a much simpler form of the integrand. So let's start by opening up the numerator. The numerator is equal to x raised to the power 4 multiplied by 1 minus x whole raised to the power 4. Using binomial theorem, this becomes x raised to the power 4 times, in brackets, 1 minus 4x plus 6x square minus 4x cube plus x raised to the power 4, which becomes x raised to the power 8 minus 4 times x raised to the power 7 plus 6 times x raised to the power 6 minus 4 times x raised to the power 5 plus x raised to the power 4. So this is the numerator, x raised to the power 8 minus 4x raised to the power 7 plus 6x raised to the power 6 minus 4x raised to the power 5 plus x raised to the power 4. And this is to be divided by the denominator of the integrand, which is x square plus 1. So we start by multiplying the denominator x square plus 1 with x raised to the power 6, and we get x raised to the power 8 plus x raised to the power 6. Subtract the two rows, x raised to the power 8 cancels, and we are left with minus 4 times x raised to the power 7 plus 5 times x raised to the power 6 minus 4 times x raised to the power 5 plus x raised to the power 4. We next multiply the denominator x square plus 1 with minus 4 times x raised to the power 5, and we get minus 4 times x raised to the power 7 minus 4 times x raised to the power 5. Again, subtracting the two lines, minus 4 times x raised to the power 7 and minus 4 times x raised to the power 5 cancel, and we are left with 5 times x raised to the power 6 plus x raised to the power 4. Moving on, we multiply the denominator x square plus 1 with plus 5 times x raised to the power 4, and we get 5 times x raised to the power 6 plus 5 times x raised to the power 4. Subtracting these last two lines, 5 times x raised to the power 6 cancels, and we get minus 4 times x raised to the power 4. Again, multiplying the denominator x square plus 1 with minus 4x square, we get minus 4 times x raised to the power 4 minus 4x square. Again, subtracting these last two lines, minus 4 times x raised to the power 4 cancels, and we are left with plus 4x square. And finally, multiplying the denominator x square plus 1 with plus 4, we get 4x square plus 4. Subtracting the last two lines, we see that 4x square cancels, and we are left with minus 4 as the remainder. Therefore, the integrand, which is equal to x raised to the power 8 minus 4 times x raised to the power 7 plus 6 times x raised to the power 6 minus 4 times x raised to the power 5 plus x raised to the power 4 divided by x square plus 1 simplifies to x raised to the power 6 minus 4 times x raised to the power 5 plus 5 times x raised to the power 4 minus 4x square plus 4 plus the remainder of the division process, which is minus 4 divided by x squared plus 1. Now this is a fairly straightforward integral to calculate. I is equal to integral 0 to 1 x raised power 6 minus 4 times x raised power 5 plus 5 times x raised power 4 minus 4x squared plus 4 minus 4 divided by x squared plus 1 dx. This is equal to x raised power 7 upon 7 minus 4 upon 6 times x raised power 6 plus 5 upon 5 times x raised power 5 minus 4 upon 3 times x cube plus 4x minus 4 times tan inverse x between the limits of integration 0 to 1. Putting in the upper limit, this is equal to 1 upon 7 minus 2 upon 3 plus 1 minus 4 upon 3 plus 4 minus 4 times tan inverse 1. All of the terms at the lower limit 0 vanish, and we therefore get 3 minus 14 plus 21 minus 28 plus 84 divided by 21 minus 4 times the value of tan inverse 1, which is pi upon 4. And this simplifies to 66 upon 21 minus pi, which further simplifies to 22 upon 7 minus pi. Therefore, the value of the integral I, integral 0 to 1 x raised to the power 4 times 1 minus x whole raised to the power 4 divided by x squared plus 1 dx is equal to 22 upon 7 minus pi. So, as predicted, this is a fairly simple integral, but it is in the right-hand side, the answer to this integral, where things start to get interesting. For x belonging to 0 to 1, which are the limits of integration, the numerator, which is x raised to the power 4 times 1 minus x whole raised to the power 4 is always positive, and the denominator x squared plus 1 is also positive. It follows that the integrand of the integral I is always positive within the limits of integration, and it therefore follows that the integral I must therefore also be positive. Therefore, the value of this integral, which we have calculated to be 22 upon 7 minus pi, must also be greater than 0, and it follows that 22 upon 7 is greater than pi. Now, we frequently use 22 upon 7 as an approximation of pi. This approximation, 22 upon 7, is therefore an overestimate of pi. Now, there is one other interesting result that can be deduced from Dalzell's integral. Again, the integral I is equal to integral 0 to 1 x raised to the power 4 times 1 minus x whole raised to the power 4 upon x squared plus 1. For x lying in between 0 and 1, which are the limits of integration, the denominator x squared plus 1 will always lie between 1 and 2. By putting in this minimum and maximum value of the denominator of the integrand, it follows that I is less than integral 0 to 1 x raised to the power 4 times 1 minus x whole raised to the power 4 divided by 1 dx, and is greater than integral 0 to 1 x raised to the power 4 times 1 minus x whole raised to the power 4 divided by 2 dx. Now, the integral I is equal to 22 upon 7 minus pi, as determined earlier. The integral at the upper end is simple to calculate. It is equal to integral 0 to 1 x raised to the power 4 times in brackets x raised to the power 4 minus 4x cube plus 6x square minus 4x plus 1 dx. This is equal to integral 0 to 1 x raised to the power 8 minus 4 times x raised to the power 7 plus 6 times x raised to the power 6 minus 4 times x raised to the power 5 plus x raised to the power 4 dx. This is equal to x raised to the power 9 upon 9 minus 4 upon 8 times x raised to the power 8 plus 6 upon 7 times x raised to the power 7 minus 4 upon 6 times x raised to the power 6 plus x raised to the power 5 upon 5 between the limits 0 and 1. This is equal to 1 upon 9 minus half plus 6 upon 7 minus 2 upon 3 plus 1 upon 5. The common denominator is 630, and we get in the numerator 70 minus 315 plus 540 minus 420 plus 126, which simplifies to 1 upon 630. And the value of the integral at the lower end is merely half of this number, that is half of 1 upon 630, which is equal to 1 upon 1260. Therefore, 22 upon 7 minus pi is greater than 1 upon 1260 and is less than 1 upon 630. Multiplying across the board by minus 1, which flips the direction of the inequality, we get pi minus 22 upon 7 is greater than minus 1 upon 630 and is less than minus 1 upon 1260. Adding 22 upon 7 across the board, we get pi is greater than 22 upon 7 minus 1 upon 630 and is less than 22 upon 7 minus 1 upon 1260. In other words, pi is greater than 1980 minus 1 upon 630 and is less than 3960 minus 1 upon 1260. Therefore, pi is greater than 1979 upon 630 and is less than 3959 divided by 1260. Which means that pi is greater than 3.14127 and so on, and less than 3.14206. The actual value of pi is 3.14159 and so on. So this range of pi deduced from Dalzell's integral turns out to be a pretty tight range. So now we have two very interesting results relating to the value of pi that we did not expect to get when we started to solve this integral. We obtained the solution of the integral as 22 upon 7 minus pi, and from this opportunistically deduced that 22 upon 7 is an overestimate of pi. We also found out that the value of pi lies in the fairly tight interval between 3.14127 and 3.14206. The actual solving of Dalzell's integral is not complicated at all. We got some practice in polynomial division along the way. The mechanics of it is not complicated, but one does have to be careful to get the right answer. So that's it. We have successfully solved a relatively simple definite integral, but the main reason I wanted to share it with you is because it unexpectedly leads to two useful results about the value of pi. That is the joy of mathematics. The mechanics along the way may look tedious, but surprising results are waiting for us if we are on the lookout for them. I hope you had fun, and I will see you back at MathMuni for the next story, where mathematics comes to our rescue and saves the day. Meanwhile, check out mathmuni.com for hundreds of mathematical problems across a range of topics, We are rapidly expanding our collection and would love to hear your feedback. Please drop your suggestions in the comments below. Bye for now.